So today I would like to talk about some work we've done at the University of Pennsylvania with my colleagues and mentors about detecting application layer denial of service attacks. So quick recap on denial of service attacks. It's an important problem. It can be a major source of revenue loss, and it can also cripple our cyber-physical infrastructure when we need them. There is a bunch of ways you can deny service, but today I'm going to focus on those attacks by resource exhaustion. And typically there are two ways to do this kind of attacks. The first one that you've probably heard about are the volumetric attacks, symmetric ones. Basically, you have a one-to-one ratio of resource consumption between the attacker and the defender. Let's say your link can tolerate 10 gigabits per second. I'm going to try to blast as much to you so that you're going to be overwhelmed and you will not be able to answer any legitimate request. Now there is a second way to exhaust resource at the defender, and those are asymmetric attacks. Those are much more pernicious and harder to detect. Basically, they reduce drastically the ratio in favor of the attacker so that with much less resources involved, I can force you to consume a lot of resources. So today, I'm going to give you a little bit of background on those attacks and deduce what are our goals when we want to detect that. As remember, like an effective mitigation needs an effective detection steps. And I'm going to introduce Finelame, which is our architecture to detect those attacks. So let me present you with a classic example, TLS renegotiation. Very straightforward. Me, as a client, can ask the server to renegotiate the share secret so that we can pursue communication. All the crypto work is going to be done at the server. This can be up to 10 times more computation expensive than for me, the attacker. Another example are what we call the billion loaf attacks. So those vulnerabilities are present in any serialization format which accept nested entities. And think about a binary tree, right? Or any tree. Like at each layer, you have an exponential number of nodes, and you're going to be able to drive up the computation for the defender like that. So what do we want to actually detect those attacks? So we gathered a set of goals. So what we really wanted is to have an online system which worked for all the resource, system-wide, and cross-components to be able to detect those attacks. So what does that mean? Let's look at the challenge brought by the asymmetric denial of service attacks. Well, the first one is that those attacks are tunable in strength. I can decide for the number of nested entities I'm going to put in my XML document so that your parser will have to take a certain amount of time to parse them. So what that means for us is that we really want per request and in-flight detection. We cannot tolerate that the request is out of the system to observe that it has committed a deed. And we cannot just monitor at the scope of the process, for example, because we would not be able to know what exactly was the critical vulnerability in our system. The second thing is that those attacks can target any resources: bandwidth, memory, CPU, cache entries. So we really wanted a system which can encompass all the system resources. Third point is that those attacks can cross component boundaries. So assume a system where you have an HTTP front-end maybe and some business logic and a database. Your request can be crossing all those different components, and the sum of the resource consumption on all those components can actually be significant. So we wanted to be able to track requests across those components. And lastly, there is an important point that the attacks can be embedded in third-party libraries. For example, TLS renegotiation attack. I'm not writing my own TLS library. Personally, I'm importing OpenSSL. And I kind of trust that OpenSSL is safe. Maybe I should not. I need to be able to track the resource consumption for those kind of libraries too. So let's have a look at Finelame. So how did we actually build up this system to detect those attacks? Well, first, the big outline is that we figured out how to build a unified system, which is doing basically 4 big things. The first one is to map application layer semantic to operating system carriers. Think about request tracing. We need to know that HTTP request 120 is being executed by PID 2000. Second is that our system allows us to monitor request consumption in flight, meaning as soon as you've been allocating memory through malloc, for example, we'll be able to account it for this request. Third, we are going to build some legitimate fingerprint of the legitimate behavior. And based on that, we're going to make some statistical analysis to be able to detect attacks on inline. So we use eBPF as a framework to build both mappers and monitor. And that allows us to have a very unified system. So you can use the same interface for both this request mapping work, this resource monitoring work, and this anomaly detection. It gives us the online properties that we wanted, system-wide, cross-component, and very importantly, it's language independent. And this is really, really practical, as we will see after. For an automated benefits, we bring some machine learning agent for anomaly detection, which is exploiting this infrastructure. So here are the main components of Finelame. So I'd like you to consider a traditional software stack where you have an application running on top of some user space library, for example, the libc, and using some kernel space library to exploit the hardware. Like, this is very standard. So at the application level, we will have what we call request mappers. The request mappers are in charge of, as soon as a request is entering a processing function, to map the request ID to the actual process ID. The second component are the resource monitors. The resource monitors are going to, each time they are summoned, and I will explain how they are summoned, track the resource consumption associated with their invocation and map it to the request ID on behalf of which the resource was consumed. Third component is an anomaly detection engine, which is going to gather all the training data, train some anomaly detection model, share the parameters with the resource monitors, which are going to become anomaly detectors. And that will allow us to perform not only resource monitoring, but anomaly detection in flight, and maintain an outlier score for each of the requests. So let's step back a little bit, and maybe it's going to be easier to see it from that perspective. What is the workflow of users using Finelame? Well, first, for the request mapping, the best person who can do that is actually our programmer. Our programmer is very good at knowing the application, she's been writing it. So she's going to register the key processing function of the application in some configuration file. So assume that the application is made of a bunch of threads, it has a thread pool, and each of the threads is performing processing events, and so we need to know the name of that function. So the programmer is going to register that function into some configuration file. Second, she's going to configure some request mappers template so that the proper request ID mapping can be maintained. The second part for the resource monitoring is handled by our service reliability engineer. This guy is very good at operating system and resource monitoring. He knows exactly that, for example, the scheduler context switch function is this and this, and he knows exactly how to measure the CPU time consumed by the previous process from that function. So he's going to declare all those resource allocation functions that he wants to in the configuration file and customize some monitors templates so that the proper parameters and values can be mapped to the request. Lastly, we need a statistic guru to do anomaly detection, and it's basically going to be about configuring threshold, like how many standard deviation away from your normal behavior you want, etc., etc. So I'm going to go over a couple of implementation highlights, which are crucial in our understanding of what were the challenge for Finelame. So we are using eBPF to do both request mappers and monitors. So eBPF is a universal in-kernel virtual machine. Probably many of you around here know about BPF. eBPF is not only a packet filter. eBPF allows you to write arbitrary pieces of code. What that allows us to do is to attach those pieces of code to any probe or trace point in your system. So for request mappers, we can have our request mapping logic associated to our key processing function. Second, for resource monitors, we can have our resource both monitoring and anomaly detection logic attached to, for example, malloc. So each time malloc is going to be invocated, I'm going to be able to grab how many bytes were allocated by malloc and to account it to the right request. Lastly, the way we can unify the system is because mappers and monitors can share the data through eBPF maps. So we maintain a global view of each request resource consumption across the system. So the very nice thing, and that's why I was so happy to say it's very practical, we had 0 line of code to change to make to neither Apache or Node.js, as well as a third system which we describe in the paper, because this is, after all, binary instrumentation. However, eBPF comes with a bunch of limitations in order to protect the kernel. It seems that either you love eBPF for what it allows you to do, or you hate it when you're a security professional for other reasons. So you cannot use loops. You cannot use floating point numbers. You have 512 byte stack for each of your functions, and a bunch of other limitations. But I'm just going to mention those right now. So let's say that now, fine-grained monitoring is relatively easy. But machine learning is actually very hard in this constrained environment. So how are we going to detect anomalies? Well, I think a previous speaker was talking about k-means as a benchmarking tool. We're going to do anomaly detection using k-means. So here is how you would go to do anomaly detection using k-means. You would take a bunch of requests as a vector in n dimensions. Each of those dimensions is going to be a resource. So for example, I can have CPU, memory, etc. And you're going to cluster all those requests in similar groups. And what you want to do is to be able to group the requests which have a similar behavior in the resource consumption space together. Now, once you learn that basic legitimate behavior, when a new request, say for example this blue star, is entering into your system, what you're going to do is to compute the distance to all of the clusters and say, okay, well, you look like you're closer to these clusters, so you're probably one of those type of requests there. And maybe based on some threshold, you're going to say, well, you're close to this cluster, but you're not that close. You're actually too far away from me, so you're an anomaly, or you're not an anomaly. So that sounds great on paper. This is extremely simple. This is probably machine learning 101. It's not even machine learning. It could be called statistics 101. Anyway, the problem is that all our Greek mathematicians are like screaming like, oh, wait, no loops? How are we going to be able to compute stuff like square roots, for example? Well, because the Babylonians had the nice methods to estimate square roots before, but it happens to be not that precise. Well, for that, we have a very simple solution. Because our resource vector are infinite amount of dimensions, the L1, which is the Manhattan distance, is actually going to be equivalent to more complex norms. So that's how we are going to compute distances, by stacking all our vectors together, or our dimensions together. Second thing, we say, well, we have no floats. How are we going to do that? Again, we have to do an approximation trick, which is to use floating point arithmetics, think about bit shifting, and we're just going to project all our monitoring data into a higher dimensional space to retain an arbitrary degree of precision on the data. And lastly, we have only 512 byte stacks. So now we are going to exploit the property of k-means, which is that it allows us to summarize the whole fingerprint of the good behavior in a small amount of points, which are the k-centroids. Basically k vectors. And the way we pick k is going to be equal to the number of branches in the application DAG. We found out that for our workload, it was a reasonably good way to map the resource consumption behavior of the system, but your mileage may vary based on your applications. So to recap, all this anomaly detection works. Well, you would collect a bunch of data from all the eBPF training maps after having let them go through your system for some time. You will train k-means, standardize. You will do that in user space. I should have maybe say that, but you can access those maps from user space transparently through the eBPF maps. You will share the parameters with resource monitors, and then you will perform anomaly detection. So I'm going to quickly go over two evaluation points that I wanted to show today. The first one is what are the overheads brought by Finelame, and the second one is a small experiment with Node.js. We have more experiments in the paper, but I just wanted to pick this one. Because I'm running over time, a little bit out of time, I'm just going to highlight two things. For Apache, we are just below 12% latency. What we did is just measure the latency of the system with and without our instrumentation. And what we observed is that once you pay the overhead cost for resource monitoring, anomaly detection comes almost for free. And that's really cool. For Node.js, what we did is we just ran an experiment with only good traffic, which we will use for training, some period of attack, and going back to normal. The load is made of 500 legitimate requests per second, and we have only one bad attack, which is more than 100-fold more expensive than the legitimate request for the attack period. We want to evaluate three things: the true positive rate, which is how can we detect all the attack requests; the true negative rate, which means how faithful are we when we are alerting you that there might be an attack; and also the speed improvement, like how long into the requests can we detect the attack. What we found out is that basically all the attacks were detected. We had a couple false positive, which means that sometimes you will be woke up during the night for nothing, but not that much. And we were able, for this experiment on median, to detect attacks less than 10% in their expected lifetime, and at best less than 5%. All right, so I'm going to finish there. The key takeaways and take questions. The key takeaways is that we built Finelame, which is a unified anomaly detection system for those asymmetric denial of service attack. It's per request and online. It's system-wide and world cross components, independent of the programming language, and there is a clear separation of concern for all the actors. I'll be happy to take questions. Thank you.
Hi, I'm Eric Eide from the University of Utah. I really like this work, and one of the cool things about it is that it can detect the attack while it's in flight, right, and do that with minimal modifications to the application being monitored.
Right.
But I think this raises a question about, well, okay, so now I know that some request is malicious. What am I going to do about it? Mm-hmm. I mean, so yeah. My application isn't. So can I respond to it without any changes to the application?
So that's actually, the mitigation is very dependent on the application model. One very straightforward thing that you might be able to do is to just terminate the request. For example, for slow attack like slow lorries, which are just staying in the background for a long time, once you detect that there are attack requests, you can just terminate them. Another way it might be to, if you have an event-driven model, you could suspend the thread executing this request kind of forever and implement a resource management policies that mitigates the resource consumption.
Thank you.
Saurabh Bakshi from Purdue. So this question is regarding your cross-layer anomaly detection module. Mm-hmm. So you are aware of these denial of service attacks which trigger algorithmic complexity bugs. So they always trigger the worst case execution paths of those. Mm-hmm. So it's not possible by looking at a single request or even a few requests to tell if this is legitimate or not, because that worst case path is indeed a legitimate request. But you can tell it's a denial of service if you see too many requests of that kind. So would you be able to handle something like that?
So I think that's not quite right. I think the problem is indeed when only one request is going to drive your resource consumption high. What we are assuming is that during your integration cycle, you will have profiled all the expected behavior so that you know that for your client, the client base that you're expecting to have, the resource consumption, or let's say the running time of a specific algorithm is going to be on average, or even its worst case, expected worst case is going to be X. But in reality, like a malicious attacker might find a way to go further. And I'm not talking about the worst case, like the algorithmic worst case of the whole function, but what you're expecting to see versus what people are actually going to do. And that's how we base that attack.
So you're also able to take into account distribution of these execution times?
Do you mean in the sense of if you have multiple people trying to attack you and doing that? No, we don't actually, and we don't need to, because if you had to consider, like there is, threshold-based anomaly detection is very straightforward. If you're on that side of the line, you're a bad guy. If you're on that side, you're a good guy, and you don't really care. It could allow you to make maybe some smarter mitigation, but not necessarily help you in terms of detection.
All
because
right,
you're
thank
good.
you.
Hi, I'm James Davis from Virginia Tech. So at USENIX Security last year, there were two different systems that were also looking at this problem. One was NodeCure, which I presented, which said, let's just kind of throw timeouts at stuff and see if that works. And the other was a work called Rampart, which was trying to do a somewhat more sophisticated thing than I did, which was kind of fingerprinting the application at a function call level and trying to learn how much or how expensive each call would be. So I understand that you're doing things at the kernel level instead of at the application level, but from a system perspective, do you think you're offering more or different security guarantees than those other systems did?
So I think that actually we have the cost of generality to pay, in the sense that you could use our system to do a base layer detection which works for a bunch of different applications. But if you were to actually embed, like Rampart did, for example, to embed the very deep knowledge of the framework into their detection and mitigation system, you're probably going to be better off. But the price in terms of programming effort and management complexity is very high. One of the things that we bring here is a clear separation of concern, as I was saying, so that the people who write the application, they just have to declare the processing pipeline. And the people who are very good at doing resource management can actually devise the resource managers. But does that answer the question?
Yeah, a little bit, yeah.
Okay, well, we can take that offline.
Sure.
I'll be happy
chat.
to chat.
Thanks.
Thank you.
Thank you.